Hi, my name is Noah Gift, and I teach data science and machine learning at some of the top universities in the world. And I also have done machine learning in production. And what we're going to cover is machine learning core concepts in 1 hour. So we're going to go through what is machine learning, how to get started, how to do exploratory data analysis, what are some of the intuitions behind machine learning algorithms, what are some things to be aware of, and then how to do classification, how to do regression, how to use the heat maps to look at the different correlated values and figure out what is working and what isn't, how to build your own features from scratch, and then finally how to kind of pull it all together and build a case study and then build out a portfolio of work. So I think this will be a really helpful refresher course or like kind of a bootstrap for you. And I look forward to having you go through and giving me feedback. Thanks. Okay, so what we're going to talk about today is just the core machine learning concepts that are involved with machine learning and how to do them. And I think maybe really quickly, let me just sketch this out. What is machine learning and why do you care about it? And what's the problem that it's solving? And so really to answer some of those questions, one thing to be aware of is the whole space of AI. And you could think of inside of AI that there's also inside of it machine learning. And so inside of machine learning, you have as well the different types. You would have supervised would be one, and we can say unsupervised is another. And then there's also reinforcement learning, which is often done with, you'll see examples with self-driving cars. And so inside there's a bunch of different kinds of machine learning. And really what's important to know about supervised is that it's historical data that you're using to make a prediction. So a good example would be looking at past stock prices to try to predict the future. And then unsupervised machine learning is clustering and labeling of the data. So you're discovering new things. So it's like you're inventing relationships that weren't seen before. So it's about discovery. Or in the case of principal component analysis, it's about reducing the noise. And then reinforcement learning is about a reward feedback loop. So that's also how, let's say a vacuum cleaner in your house, one of those RoboVacs goes around and it vacuums, you're using this reward feedback loop and you're training it to advance. So that's really the overview, but let's get into some of the actual concepts and code. To start with, one of the key statistical concepts for machine learning is this idea of correlation, both exploratory data analysis and feature engineering. Really use the concept of correlation, where if you wanted to discover what features to use, and we'll get into this in a second, let's say I wanted to discover influencers on TikTok. How would I do that? Well, I might find two features that are correlated, and that could add a prediction strength that would tell me, who's popular. Also, we need to know about nonlinear and linear relationships in order to properly fit a model. And so this is an important aspect of doing machine learning, is understanding those nonlinear and linear relationships. So related to these statistical concepts is this idea of the law of large numbers. And a lot of times what happens when a gambler is at the casino, they'll see, for example, the roulette wheel that black is hit 8 times in a row, and then they'll be convinced that if they just put their money on red, that they can win a lot of money because it's due to be hit. But that's not the way that the law of large numbers works, is that there may be peaks and valleys, but every single observation has an equal chance of appearing. So some of those same concepts appear when you're dealing with machine learning. So the larger the data set, the more you can predict about the future. And that's really what the law of large numbers says. And the same goes with an index fund, right? You're averaging out all of the noise by investing in lots of companies. And the result here is that the average of the results obtained from a large number of trials should be close to the expected value as more and more trials are performed. You also see the same concept with flipping a coin, right? If you may have some spikes where you can flip the coin and it hits 4 times in a row, heads, but over 1,000 observations, there'll be about 50% of tails and 50% of heads. Another concept that crops up a lot in machine learning and doing plotting or fitting is this concept of smoothing. And so here's an example where I grabbed some stuff from an example from Stack Overflow that you can link to. And really all this does is it shows how you could fit to a global function. And if I click on this and we run it, what happens is that you can see that there's a unsmooth curve that looks like this, right? And then you can see that there's a smooth curve. And the whole idea here is that when it's smoothed, that you can do a better fit of a function and get a better prediction. And so that's a lot of what we're doing as well with machine learning is we're trying to fit things to the right line so we can predict where things will be in the future. You know, we've seen this recently with the stock market. You know, it could be very important even in an hourly basis to know what direction the stocks are headed if you're a day trader, because you could lose a lot of money or you could gain a lot of money. So you want to fit the direction things are headed. Let's talk about another key concept as well, which is what I talked about earlier, which is supervised machine learning is historical data is used to do a prediction like a linear regression. Unsupervised is patterns. And then a couple other things that are important that are often not apparent until you start to get into machine learning is that in order to do machine learning at all, the data needs to be numeric, right? So if you have categorical data, if it's red, blue, green, for example, you have to convert that to a numerical format or else the machine learning algorithms won't work. Likewise, almost all machine learning algorithms, not all, but most of them require some kind of scaling so that you're comparing apples to apples. Like for example, with clustering, if you don't scale the data first, what happens is that there could be distortions with the data because certain fields are, you're not comparing apples to apples. And so you're getting problems in terms of the scaling. So now let's get into really what would be important to a business student is thinking about the feedback loop. If you're implementing machine learning in your company, well, how would you do this? Well, the ideas are that first you would collect the data, and that's, if you don't have data, you can't do machine learning. And then the second one would be to get into exploring the data, so exploratory data analysis, and then preparing the data. And this can actually be 80% of the work in most scenarios, and it's quite a big task. Once you're done with it, then you could train the model, evaluate the model performance, so get the model into production. This would be something called ML Ops. Improve the model performance, and then apply DevOps best practices. So this concept of incrementally making improvements or Kaizen. And let's look at a real world machine learning pipeline here. So this is something that I developed for a company in 2013. And what we were trying to do was predict the influencers. We dealt with influencers just like there's influencers today on TikTok and Snapchat. We were looking at influencers on Twitter and Facebook. And what we did was we collected Twitter data, we collected Facebook data, we collected Wikipedia data, and then we also collected our own data for how those influencers were performing on our platform. And so this is where the correlation would come in that I talked about earlier, is that these features were correlated with each other, and they were also correlated with the page view. So what that does is allows us to do feature engineering. So we picked these 3 features to try to predict how many page views they would bring onto our platform. So this collection job really was very complicated. And part of the reason it was complicated was that we first even had to ask Mechanical Turk to find out what were the actual labels for Twitter, Facebook, Wikipedia. So what were the real social media handles of all these influencers? Once we did that, then we put the data into Amazon S3. So it was storage, and that was a decent amount of work. Now then the hard part came, which was, so okay, I think that this is going to give us a model, but we need to go through and explore the data, plot it, use Jupyter Notebook, use some plotting libraries, do some clustering, do principal component analysis, all kinds of techniques. And this took a lot of work right here. And then if we scroll down, this was only 5% of the work. Once I got to the point where I was able to collect the data and do exploratory data analysis, then I knew that the model was actually fairly straightforward. And to train the model, I tried out 3 different regression techniques. I used K&N regression, ridge regression, and log regression. And then finally, in order to evaluate it, I used my performance metric was root mean squared error. And then finally, I wanted to improve the model, so I was constantly comparing it with other algorithms. So this is actually, I think, something similar to the code I finally put into production. This is in the language R, but it's fairly readable because it's like high-level code. So you can see I combine all of this data from social media, Facebook, Twitter, Wikipedia. I have here an analytics file, and it combines the data. Then what I do is I use this fit. So I use the K&N regression to go through here and tune the model, get it working, and then I read in the data, clean it up, create the test and training set. So it gets split right here. I add a grouping column, and then finally I calculate the prediction value. So I figure out if my model is getting more and more accurate. We want the error to be lower. So let's take a look at what that would actually look like if I plot this. So here's some Python code where I grab in really core libraries in Python, and I grab in this data set, and you can grab this data set yourself if you want to take a look at it. And this gives us what we're taking a look at. So you can see here we have the Twitter rank. So this is how, of the observations that I have in this data set, what is their rank on Twitter? What is their rank on Facebook? What is the maybe another rank, like the rank on Wikipedia, and how many page views have they generated on our platform? And then how many times have they posted content on our platform as well? And then what is the median amount of page views that they've generated, right? So I have some good statistical data, and then I can go through there and play around with it. So that's really the basis of that particular model. So let's talk a little bit more about some of the concepts, and then I'll get into examples. So, I guess the idea here is that when you are building a prediction system from the beginning, the linear regression is the 800-pound gorilla. And the reason why it's the 800-pound gorilla is never a bad place to start. And even if I guess you can even think about it as a form of exploratory data analysis, right? Like, why not try linear regression, look at the diagnostics, and see if it will give you anything. And even against some nonlinear data, it actually performs okay. So that's the nice thing about linear regression, is even if the data is super linear, it can still give you a reasonable first guess. And so what are some of the things that you would use linear regression for? And one view of machine learning is that ML consists of developing regression models with a prediction goal. You can also predict continuous variable, and you can forecast the future, right? So the idea here is we have all this noise, we have all these observations, and can we figure out the true line? Like what is the prediction that's going to have the lowest accuracy that we can generalize across all observations? And in the libraries available are quite large. You know, in Python you have scikit-learn. There's tons of different libraries. There's ordinary least squares. There's ridge regression. There's lasso regression. There's Bayesian regression, robustness regression. In R, there's a caret library. Basically, there's tons and tons of libraries that you can use to do linear regression. But the big takeaway is that the reason it's a little bit different in machine learning is that they use cross-fold validation as one of the techniques in particular. And what cross-fold validation can do is reduce the overfitting, which is you're making too aggressive of a prediction and you fit too closely to your training data. So cross-validation, by splitting the data into a bunch of different observations and then doing it multiple times, you can reduce the overfitting. And then also with linear regression, you would use root mean squared error versus traditionally in statistical linear regression, you would look at things like p-value, like is it significant, or R squared. So if we go down to ML regression example here, let's walk through how you could actually do a very simple linear regression to get the concepts down. So here's a pandas import, and then I read in a data set that's a very simple data set. It's the name of a baseball player. Here's the name of the team. Here is the position. Here's their height, and here's their the weight, and here's their age. And so if I run df.shape, this is very common when you're first working with a data set in exploratory data analysis, is look at the shape of the data. So how many rows are there, and then how many columns? And then also, are there any null values? Because those can cause problems when you're doing a prediction. So what we can do here is we can drop the null values, and then notice that there's one row got dropped, right? So really pretty small amount of data to be dropped. And then this happens as well, cleaning. We may want to rearrange the column names because they're annoying, because they're too long, or they're named something we don't want them to be named. So you can rename them by using the pandas rename function. There we go. And now you can see that it looks a little bit cleaner. Okay, we've got that cleanup done. Now let's describe the data. And you can see some very good observations about what's happening by using the describe. And in particular, what we can look at is you can look at things like, what is the median height? And so in this case, 74 inches would be the median height. And so if you took 12 inches times 5 would be 60. 12 inches times 6 would be 72. And so these baseball players are actually fairly tall. The median baseball player, it would be about 6'2", and their weight is about 200 pounds, and then their median age is about 28. But then if you look at the max, you can see that the max is there's actually some very tall baseball players, and so that would be 6 foot would be 72, so that would be 6'11". You have a 6'11" baseball player, and you have some that weigh 290 pounds, and even baseball players that are almost 50 years old in this data set. So let's go through here and look at how to model this to do a prediction. So notice I say from scikit-learn, import linear model, from scikit-learn.model, import train test split. And then what I do is I look at the shape, right? Because I just want one variable to do the feature. And then all I do here is I just create a target, which is what I want to predict, and then I create the feature, which is the value that I'm going to use to actually give the signal to make the prediction. And then we can look at the shape. And those should match, right? There should be the same number of rows in both. And then we split the data. And the reason that you split the data is so that you're pulling the data out into a section to train it, and then a section to test it. If you only train the data and you don't have a test data, you'll overfit because you'll have generalized too much to the training data set, and you won't be able to generalize to a larger set of data. And so this is the approach that you would use. You'd say split the data. And then finally, we're ready to do a prediction. And to do a prediction, I create an instance of LM. I then do model.fit, and then I generate my prediction, right? And so that's really it in a nutshell of how to do a prediction. And if you want to look at the prediction, you can kind of play around with it a little bit and see, for example, that it's a NumPy array. So we got the prediction, let's plot it. So to plot it, I can actually go like this. I can say from matplotlib, basically plot what the actual weight was versus the predicted weight. So you can see here's the predicted weight, here's the actual weight. So you can see that there's definitely, it's on the right track. It's not perfect, but, and there's some outliers. For example, this one was a little bit too high over here, but in general, you can tell there's a linear trend. And if we look at the accuracy here, we can see that this is my my accuracy score. And so if I wanted to put more and more things into it or change the algorithm, then I would want to get that score lower and lower in order to improve my model. I could also use different models, like, for example, Lasso Regression, which is another type of regression. And so if we go through here and I go through it, you can see that it gives me some diagnostic tools and shows me the different regression techniques. I can also use cross-validation. And as I mentioned before, there's no guarantee that cross-validation will improve the accuracy, but it might. And so we can try that out, and we import that, and then we look at what the scores are. And we can even look at each of the folds, what were the folds. And you can see that there's actually, in this fold, it was actually very good. It was actually pretty low, but then there's another fold that's pretty high. And then we can go through and we can plot the cross-validation predictions as well. And then again, look at the accuracy, and we can see that, okay, we did actually slightly improve, just a little bit. We improved the accuracy by using cross-validation. And then we can also go through and use a library to visualize the cross-validation scores as well. And you can see that across all of these different training instances that there were some that were very accurate, relative for this particular model, and then some were like, double the error rate. And so we can maybe use that to further diagnose and figure out other techniques that we could play around with. So there's lots of things you can do with just a really simple linear regression to constantly figure out how to make your model more accurate. So the conclusion is that in this particular example, that cross-validation did improve accuracy. Adding more data or features could improve the model. And then Major League Baseball, though, may be a weird data set to predict weight because they're very unusually large people. So it may not be something we would want to use for the general population. Okay, so that's linear regression, but now let's talk about another type of prediction, which is a classification. A classification is I'm trying to pick which category something is in. So, is it true or false, or is it toxic comments or not toxic comments, or is it the red color or blue color or green color, right? Those are all kinds of classifications. And one of them that is commonly used in spam filters is called a naive Bayes classifier. And it uses the Bayesian probability. And you can see what this is, the equation for it, but the intuition is probably a little easier to explain by explaining this Monty Hall problem. And so the way it works is, suppose you're on a game show and you're given the choice of 3 doors. Behind one door is a car, behind the other is a goat. you pick a door, you say number 1, and the host who knows who's behind the doors opens another, maybe the third door, and says, they have a goat. And then he says to you, do you want to pick door number 2? So should you switch your choice? So basically, the core of the problem is that now that you have new information, like in the fact that one of the doors actually doesn't have the goat behind it, should you pick again? And so over time, you should. And in fact, this shows you exactly the math of how that works. Is you can say the doors here, the change wins, change loss, and you can basically randomly simulate those events. And we can see in this particular example that if you change the door, you would win 66% of the time. So you increase your probability. At first, you only have a 1 in 3 chance, but then if you always switch your choice over the long haul, you would have 2 out of 3 chance of winning. So this is really the intuition behind Bayesian probability. So how can we use this? We can use this to classify text, and this is a good example where let's say I want to go in and do some text classification on news groups, right? These are from the built-in data sets with scikit-learn. So in order to download those, you just click this button and it goes through, downloads the data sets, and we have religion, we have Christian religion, we have space, and then we have computer graphics. And so if we run this, it gives us one example of the training set, and you can see it's kind of a silly data set. Or this one, somebody's talking about nuclear waste, and we have a conversation here. So now let's go through and train the model to predict what category of text it is. Is it Christian? Is it religion? Is it maybe space talk? And so how do we do this? Well, we import something called TFID vectorizer, which allows us to manipulate the text into a form that we can do machine learning on it. As I mentioned earlier, that all machine learning requires you to convert it to numerical format. The next thing we do is we use something called multinomial naive Bayes. So we're basically, it's a fancy way of saying we're going to use Bayesian probability to predict multiple categories. And then we go through and we do the same thing we did earlier, is we say model.fit, train data, train target, right? So we go through here. And then once we do this, we can look at a confusion matrix, and this is built into scikit-learn metrics. And this confusion matrix will show us of our predictions, right, which ones were really good and which ones were not as good, and what categories were we able to, did we have some confusion with. And in particular, if we look at computer graphics here, this appears to be very highly accurate, like in terms of the predictions here. So we said 344 of these came out the way we would expected. There's only a very small amount of confusion with space and a very small amount of confusion with Christian conversations. And then also, if we look at space here, we can see that it also is very good, right? Is that we have very good classification metrics here and only a small amount of misclassifications. And then even better is the Christian religion is so unique, I guess the terminology they use, that it's not common to confuse it with other topics. Like in fact, regular religion, it was not confused, only a little bit of confusion here. The one that was the most misclassified though was, in this case, religion itself was misclassified with the Christian religion. And so we could kind of look through here and maybe train our model to predict things, in a different way or add more data. But the general idea here is that what's useful about this example is I take data, convert it to numerical format, I then classify by splitting the data between the training data set and the test data set, and then I do a prediction. And so if we want to look at just kind of play around with the data a little bit, we can even start putting text in here, and I can do my own predictions, right? So okay, sending a payload to the International Space Station, look, it found what it was going to predict. If I said discussing Islam versus atheism, it predicted the religious Christian. If I go through and I say determining the screen resolution, it predicted computer graphics. If I did, this is a large visualization, it predicted, the right category, which is computer graphics. So that's a pretty fun data set that's really simple to play around with to get a feel for text-based classifications. So and you can see there's some references where some of this that those results came from. Now, if you want to try other ways of playing around with this, there's other libraries like in the cloud. There's Blazing Text Algorithm. There's topic modeling with Gensim. There's topic modeling with AWS Comprehend. So there's other cloud-based models that are often used as well. And there's some discussion questions to play around with. So let's move on now to another topic, which is clustering, which is an unsupervised topic. And in particular, as I mentioned earlier, unsupervised machine learning is a technique that allows you to discover hidden labels. So really you're looking as a detective into the data, and you're trying to find out what you can discover about the data. So let's take a look at something that's very interesting in the United States. There's lots of different markets that have maybe regressive taxations or hyper growth, and there's lots of different price changes. And so what we can do here is import some libraries that are very common, right? Pandas, the stats library, things like that. And then what I do is I go to Zillow Research, and I'll just take a look at this link real quick. So if you look at Zillow Research, you can download lots of different kinds of data, like the rental data, inventory, sales. You can really find some great data here. I grabbed the home value data set here for single family homes, and then I actually clicked this link. So from here I can just say pandas, read in this data, and then this will pull in this particular data set and then put it into a pandas data frame. And you can see the values here. We've got regions, size rank, region name, the states, the cities, great. And now if I wanted to cluster that and figure out some hidden secrets, how would I do this? Well, first I clean up the data. So I go through here and I say dataframe.rename, the region name to zip code, and then also drop the region ID. I don't want that. I also don't want the region type. And then look at this, the first few rows by using df.head. And you can see here that I changed the zip code. So that's helpful. And then if I want to play around with the data and do more explorations, let's say I'm working with a client or I'm working with my boss, then I would maybe go through here and look at things like this. Like here's the median prices for all of the United States for 2021, 131. You can see that the median price is 178,000. And in fact, it looks like it's gone up very significantly, even from, if we said tail, let's look at the last 12 months and let's see if something unusual is happening. So, you can see that like maybe at the beginning of COVID-19 that things only went up maybe like 1,000 per month in median price, but then all of a sudden things started to get faster, right? We can see, for example, the last few months, the housing market in the US, the median housing market has really expanded. They lowered interest rates. And then we could even look further if we wanted to, is we could look at things like, the median housing prices for the San Francisco, Palo Alto, and then compare them. So that's what we're going to do. And so I'm going to use a library called Plotly. And what's nice about Plotly is it allows me to do interactive 3D visualizations. And for business analytics in particular, this is a great library to explore ideas and share things with people. So I import those libraries, and then I have to run this piece of code, which enables Plotly to run. And then I put a title for my visualization. So I say regressive taxation and single family zoning 1994 to 2021. So this is my opinion, is that the US has regressive taxation, which means that the rich people in the United States, they get richer, and then the poor get poorer. That's basically what regressive taxation is. And then we have the year, and then we have a sales price. So if I run this, and what we can see is a very powerful visualization that really puts things into perspective, right? So if I was going to the government of the United States or to a local part of the United States, I would say, hey, what's going on here? Look at this. Back in 1996, things weren't that different. I mean, there's more expensive areas to live in the United States, but things were relatively comparable. But right around 2000, there's been an exponential growth here of Palo Alto real estate. And look now that Palo Alto, the median value is 3.4 million. So who are these people that could even afford a median house in Palo Alto? They would have to have very wealthy people, like maybe making $800,000 a year or $1 million a year to be able to afford a house that's that expensive. But then look at the rest of the United States. You can see it's barely changed, right? From back here in 1994, houses were like $100,000, $108,000, and now we have almost over 30 years later, we have basically it's only gone up, not even in a linear trend. It's a sublinear trend, or at least a very gradual linear trend here. And so there's something very different happening in the San Francisco and Palo Alto, and part of it is there's tax laws that encourage people to have home prices go up. And then if I want to look into this further, what I can look at is the clustering on size, rank, and price. So I first have to scale the data. I mentioned that earlier. Almost all machine learning, you have to scale it first so that you can compare the apples to apples, basically. If you have one column that's miles and another column that's feet, it will distort everything. So you need to convert that so that it's relative. And so I go through here and I drop these columns, because these are non-numerical. So I have to get rid of all the text. And then I go through here and I verify it, great. I then do a description. You can see that these are all numerical here, right? And now I do the scaling. So I go through here and I scale my data, and then I put into the scale data I put the scale data into the k-means clustering. And to do k-means clustering, I tell it, here's my number of clusters. And then what'll happen is that it shows that I was able to cluster 12,000 results. And now what I do is I change the data around here so that I can get a good feel for how to do a data visualization. So for business analytics in particular, or data science, that the clustering is helpful to discover the hidden data, but then I may need to add other pieces of the data, like let's say the appreciation ratio, or I want to add something like the city, the zip code, and the appreciation ratio. So I add like a piece of text so that when I scroll over it, I can visualize where I'm at. So if I'm presenting this to the business leader, they know what's happening. So we're going to go ahead and do that. And then once I do this, I'm ready to again do a data visualization, but this one will be a three-dimensional data visualization. And so each of the clusters will be plotted. I also put in that special piece of text here. I say what the text is. It's going to be the city zip code ratio. And then I put in the titles, appreciation ratio, the 30 years of history of the US, and then I do this plot. So let's go ahead and plot this. And when I do this plot, we find some very fascinating data that would be difficult to see if we weren't doing three-dimensional clustering. And in particular, that what we can see here is that over the last 30 years or so, that the appreciation ratio, so there's essentially three clusters. The first cluster is the regular United States. These are all like normal places, essentially. This is middle America, middle class people, essentially. And we can see that, look, these are all places if you want to live a middle class life, maybe this is where you should live. We have Philadelphia, Atlanta, Sacramento, these are all like Boston. Nothing too crazy is going on here, because even though the appreciation ratio has gone up a bit, that they're still, in relative terms, these are all homes that are under $1 million or so for median. But then if we look at this purple cluster here, the appreciation ratio is off the chart. So it's double the appreciation, right? And so look at this one. This one, Santa Monica, which is the beach part of Los Angeles, has appreciated 16 times. So in 1994, if you bought a house in Santa Monica today, it would be worth, if you bought it for $150, it would be worth $2.4 million. So that's really pretty incredible in terms of how much it appreciated. And they do have the regressive property tax laws in California, where you don't have to pay property taxes at the rate that they're currently worth. You only pay the property taxes based on what you originally bought it. So it's really it's basically socialism for the rich. And then if we look at this, we see San Marino, which is a neighborhood right next to Caltech, also incredible appreciation ratio. Beverly Hills as well. So these are extremely high appreciation ratios. But then there's a third cluster, which is basically the 1% of the United States. So these are neighborhoods where the truly elite and wealthy live. And in fact, who is the most elite and the most wealthy in the United States would be this zip code, which is Atherton. And Atherton is a zip code in Palo Alto. And I've been there I've been invited to dinner parties in Atherton before. And you can see like maybe a 2,000 square foot house would be worth, $7 million. So there's a very weird, distorted area in Atherton where if that same house, you brought it to, let's say, Atlanta, Georgia, the house would probably be worth maybe $700,000. So there's a very distorted happening in the United States. And again, we get to discover these labels as a data scientist. And I would probably label, the elite, the global elite, the 1%. I would call this, maybe places where the regressive taxation has really, they've enforced certain zoning laws, or they don't have to pay property taxes because they're grandfathered in. And then this cluster would be like middle class people. And so it helps us doing machine learning discover really interesting information. And then we could also write this into a report and then have a conclusion that maybe told the government of California, hey, you have one of the largest homeless populations in the world. And one of the reasons for this is that you have created regressive laws. And in fact, if you looked into cities like Santa Monica in particular, the homeless population is just incredible. There's people that are living in the streets everywhere, and part of it is just bad government policy. So let's go through to the next section here, and let's also kind of look through some other things you could do. You could also then, if you wanted to, do regression and try regression if you wanted to. So this is a good data set to play around with and go further and do more stuff if you're interested. So we went through a lot of techniques, but another thing to bring up really quickly here is that even if you do write code and you're fluent in all the stuff that I showed you, another approach that is very common is to not worry at all about doing machine learning where you write all the code yourself. And so I'm just going to tee that up for a second, and we'll come back to it. But there's Google AutoML tables, there's Amazon machine learning, there's Azure ML Studio, all things I've used to do machine learning as well. And a lot of times you can get very, very good results, just like the results I showed earlier, by using these no-code tools. And so if you're a business student, for example, and you don't want to write all that code that I showed you, you can also do similar things with these off-the-shelf tools. But let's come back to that. Let's keep going here and talk about some of the ideas in machine learning. So supervised machine learning, as we talked about before, here's some of the trends from the 1800s to 1980. These were really linear models. These were the only option before there were computers. And 80 to 95 neural networks, so multi-layer perceptrons. The success was limited to small data sets. 95 to 2010 linear models like SVMs. And then right now, neural networks, a lot of research is happening with neural networks. And what we can see here is that, as I mentioned earlier, a lot of these other trends now are coming to fruition, like model explainability, managed machine learning systems like SageMaker, AutoML, H2O, Ludwig, AutoML, GCP. So that's probably the biggest trend now is currently is how do you explain what's happening, and then also how to use high-level systems. And here's an example of how an AutoML system would work is, and we'll do a demo in a second, but you would have the table data, you define your schema, you tell it to look at the features, it trains the model, evaluates it, deploys it, and it's all by just clicking the console inside of Google Cloud. So let's talk about a couple more topics here as well. So support vector machines. Here's a visualization here that the idea is that they maximize margin. So decision boundary with largest margin gives best generalization. Support vectors are the data points that define the margin, and the problem of finding the line with the maximum margin can be solved efficiently. So that's one of the newer approaches here. Is it's taking all these different vectors to find the optimal relationship to split something up, to make a decision boundary. And if we look at classifiers as well, another thing to be aware of is that these support vector machines are harder to understand than decision trees, and also other things to account for: model size, the training inference speed. So are you using GPUs, for example? And then there's also the no free lunch theorem, which is no universally best classifier. A classifier may be the best for some problems, but not for others, and you should try a few different methods. So, and these are all things that are ideas, I think, that come from when I taught a class from UC Berkeley and some of the staff there, and in particular, scikit-learn classifier. Here I go through and I import a bunch of different types of classifiers, and this is actually comes with the scikit-learn. This is an example from their documentation, and if I take nearest neighbor, linear SVM, Gaussian process, decision tree, random forest, neural net, naive Bayes, all these different classifiers here, and I do the same thing I did before. I try a bunch of these classifiers here. Put them all into this list. I can say try with all these different data sets. These are built-in data sets into scikit-learn. Go through and plot all of them and show me visually how they all work. And so if we just scroll down here and we look at the example, you can see that basically it shows you that different classifiers are better or worse depending on what the problem is. So in the case of, here's my input data, you can see that this particular data set is got some overlapping data for the boundary, but this one's pretty clean. So we can see that nearest neighbor here is pretty good, but maybe the Gaussian process is better because Gaussian based it has the ability to be a little more like more like settled boundaries with the Gaussian. You can see a decision tree. We can see exactly how this works. So in a nutshell, or a neural network, you can see examples that if you want to get an intuition behind how one would work versus another, this is not a bad chart to just kind of compare that you can look at to see how you could use these different approaches. Okay, so that's kind of some of the theory, and now let's get into some case studies and real world examples here. So one thing I'll bring up is that in the real world, this feature engineering or deciding what label data to use is often like a mess where, and this is actually from an O'Reilly book on feature engineering. That's a good book. If you go through here and you kind of try to find the correct answer, it's going to be a long, winding road. And so it's full of false starts, delays, infrastructure problems, laptop problems. So like your laptop isn't production, right? It may not be able to deal with the size of the data. And then the real world isn't a Kaggle data set or MNIST data set. And so some of the core aspects of machine learning are it's a model, mathematical model that describes the relationship between the data, and a feature is a numeric representation of the raw data. And so here's another picture from the same book, and you can see here that here's the sources. You have to select and merge. Here's the raw data. I transform it. I build this into a feature, and then it's at this point that I can do the model. And then once I create the model, then I can go through and then come up with an insight. And in particular, there's another example here of how in a real world machine learning system, we have configuration data, data collection, feature extraction, data verification, but the ML code is a very tiny piece, and all these other pieces are really the pieces that take a lot of the time. And this is why in real world machine learning, the actual prediction is a very small amount. And that's why ML ops is a hot topic right now. So some of the takeaways here, again, real world machine learning system, this is all the glue code is the sundae, and then the ML code itself is the cherry on the sundae. It's the last piece that's actually being done. All the other stuff is what's happening. And here's another graph that I think is a good graph. Is you can see that data scientist is kind of research oriented, but a machine learning engineer is operational oriented, and then a data engineer is more computer science oriented. So that's another way of thinking about what's happening. And I think this is another metric, is that there's 4 to 5 data engineers per data scientist. A lot of people have been saying. So let's look at now in practice, how could we do some feature engineering? Well, one of the ways we could do this is I'll pull in a data set from FIFA, and this FIFA data set will have the man of the match, which is basically the most valuable player. And so if I look at this and I print it out, you can see here that it has like the goals, how many goals are scored, what the ball possession is, how many blocks, corners, offsides, free kicks. So what we're going to try to do is predict who would be named the MVP or the man of the match for that particular game. And so what we could do is we can install a library called ELI5, which stands for Explain Like I'm 5. And we'll go through here, install this. And then in particular, what we can do once this is installed is use something called Permutation Importance. And what Permutation Importance will do is it'll take my model and then it will show the weights. So it'll show of the model that I created, what were the features that were the most important. And the way it does this is it takes the feature out and then calculates the prediction and shows the delta of how important that feature was. So by subtracting that feature, you can see how important it was. And you can see that the most important is goals. So if you score the most goals, you have the highest probability to be named the MVP or the man of the match. Distance covered is a secondary characteristic. So if you're one of the most active players in the game, that's a feature. Yellow card is a positive correlation, which is kind of interesting. I guess maybe if you're very aggressive, then people like that. And then also you can see some of these other ones. Now, what's funny is that basically what this is telling you also is maybe don't pass the ball as much because it's negatively correlated. So if you play selfishly, then potentially, you'll have a higher probability of being named the man of the match. And then, as I mentioned earlier, scaling data is something that really is important. And so to be safe, always apply mean and variance scaling to the feature values. And so what we're going to do next here is we're going to look at a feature engineering problem where I have some data from the MBA and also some housing data right here. So this has got like attendance of games and then also, basically the valuation of the teams in the area and then how good the team was, which is this ELO score. And so to prepare for clustering, what I would do is I would say I want to cluster on 4 columns: the attendance in the stadium, how good the team is, the valuation, and median home prices. So now I'm kind of taking a problem that was maybe I explored initially with housing, but then I'm combining the data sets together. And here I have to create a numerical data set, right? We talked about that. We also talked about scaling. I have to scale it. And look, when I scale the data, see how it's all between 1 and 0 now, right? Because I said between 1 and 0. And then I go through here and I run a clustering algorithm and I say, I want to have 3 clusters. I want to fit it. And then what I do is I grab this thing, k-means.label, and then I put that k-means label onto the very end. And you can see that I assign these clusters. And now if I want to plot this, here's a plot in R that's a little bit hard to see. But basically what this does is it then also teases out some interesting data where that really what we can find out is that even though a team may be very good or very bad, that it isn't the main driver of why a team is valued highly, because in this particular column, the further you are to the right, the more valuable the team is. And look, the ELO is how good the team is. The higher it is, the better the team is. That this cluster are very highly valued teams that are very bad. This was before the Los Angeles Lakers had LeBron James and Anthony Davis. And so this shows us that the true driver of valuation for the NBA teams is real estate value, right? And so if there's high real estate value, and so we have 3 clusters in this particular example. We have a cluster which are basically average teams that are very low valuation. And then we have a second cluster, which is basically good teams. And then we have a third cluster, which is bad teams, which are highly valued. And you can play around with that data if you want there. And then if we want to look at a 3-dimensional real-time plot, we can look at this plot. And what this will do is show us that we can do something similar. So in this particular example, we can play around a little bit with the data and see that, again, that there's a very distinct clusters here that, if we see the valuation, these are the high ones, the Los Angeles Lakers and New York Knicks, that they're actually, if we scroll down here, the ELO is this one. So these are very poor performing teams. But then if I scroll over here and I look at ELO, we can see that the Golden State Warriors at the time were very highly rated, but look, their valuation is still not as high as this cluster. So we have basically 3 totally different kinds of teams in the NBA, and by combining different data sets, we can get this new relationship and expose those with machine learning. And so just a few other takeaways about machine learning here is that there are many different kinds of biased, unbalanced ratio of positive to negative. This may cause a classifier to pick the majority class, mismatched sources, training procedure that's focused on the training data. Maybe an algorithm won't work well with the data. And so a few takeaways are that if you have 1,000 to 10,000 training examples, maybe try complex algorithms. But the more data you have, the harder it will be to beat logistic regression. And neural networks can discover useful features in complex inputs like images and speech. And that's why people are doing deep learning for things like images and speech. And a good place to start when you're looking at doing machine learning is this. It's like a guide, basically, is, if you start off and you have more, if you have under 50 samples, get more data. If you have over and you want to predict a category, then do you have the labeled data? So if you do have labeled data, then you can go through here and you can try maybe the linear SVC, and then you can go through this whole tree. Same wise, if you're not predicting a category and you're predicting a quantity, and you have less than 100,000 samples, you pick, a Lasso Regression or Elastic Net. And so that kind of an approach where you look at the chart to choose which approach I think is a good strategy. So we'll wrap up with two things here. One of them is, let's go into how you would predict a team. And so here I have that same MBA data set. I grab in their data here. Let's say I wanted to make my own feature, right? So I want to create a new feature, which, if you notice here, we don't have the concept of a winning season. We just have basically how many games were played inside of here. And so what I would want to do is I want to change this feature. I want to write a function that says I'm going to take the number of wins, and if the wins are greater than 42, then I'll return a 1. But if they're less, I will return a 0. So I'm going to basically create a feature that's binary. It's either a 1 or a 0. And then I'm going to apply that function here and say a winning season we would take the W here and we would build it out. So if I run this, what'll happen is you can see the plot is that all of these teams now have a losing season, and the winning season is over here, right? It's much harder to have a winning season. And we also can see that there isn't really a relationship between the age and whether you have a winning season at all. There's no correlation. It's equally distributed. That in fact, you could even say that, like, it looks like up here there's even some relationship with when you're a little bit older, maybe you're more experienced. So how would we predict a winning season now that we have this new feature? Age, points, salary, page views. If I grab all these different values, I'm going to put those into two classes, which is winning and losing. And I do the same thing that I did earlier. I say from scikit-learn.model selection import train test split. And so I go through here and I use logistic regression, which is a way of predicting classification. Go through here and I fit the model. There we go. And now what I can do is I can say, well, let's look at a report here that shows a classification report, and we can see in this case that we have losing, we have winning, and we can see the different metrics like false positives, false negatives, right, that all appear with precision, recall, F1, and support. So I was able to create a successful winning season classification. We can also rank this by using feature ranking with Yellow Brick, and that gets into the exploratory data analysis. For some reason that one blew up, so I won't run it. But let's look at this thing called shape, which is also a feature explanation. For some reason, I need to pip install it. So let's go through here and we'll say pip install this library. And what this library does is allows us to basically explore which features are the most important for classification. So let's go through here. Let's run this. There we go. And what it should show us is that there are non-intuitive features that are very important. So the salary turns out to be a really important feature. How popular they are on social media turns out to be an important feature, whether they would have a winning season. So maybe what this means is that the fans are attracted to successful basketball players. And then we can break this out even further. And if we look into this, we can see that, in fact, these are the different, the values, high feature value, low feature value. And so again, you can see that Twitter favorite count here is really got some very strong predictive power here. And then if I do a bar plot, this might be a little more simpler, is that of the features that impacted whether the NBA team had a winning season or not, that the Wikipedia, which is like a Wikipedia page views, which is a popularity rank, and Twitter were more important for predicting whether a player would have a winning season than even how much they got paid and even their on the court performance or their age or even another on the court performance. So that's why feature engineering is so important to be aware of, is that it can show you things that are non-intuitive. And if we look at one more, right, we can see like the ELI 5, and again, it shows us, based on these are the core features driving the model. I won't run this one, but there are some other models approaches you can use. Like you can use H2O, which is an auto ML system that can also go through and just do everything for you and pick a bunch of different models. And the way it would look would be something like this. If we scroll down, and it would just run through like every single model that becomes available, and then shows you which one is the best model. I think there's some merit to the AutoML approach, which is why write a bunch of code if you can actually tell it to look for a particular thing and it goes through all the different variations for you. So really that's kind of where I wanted to end in terms of this particular piece of code. And next, I just want to show one thing, which is in terms of AutoML, that something to be aware of. If I go to AutoML tables, is that you can also do classification by using these cloud-based systems. And in particular, a good one would be, here's a data set that I played around with earlier, which is predicting your income. And we can look, I could just import a data set by uploading a CSV file, and then it goes through here and it allows us to, essentially go through and choose the columns, pick the target, like does the person get married or not, or how much money are they going to get. I can pick anything I want, and then if I go to evaluation, we can see that it gives me this whole breakdown and shows us like the accuracy of how it was able to perform in terms of predicting the income and all the different performance metrics. And area under the curve is 0.83. So I could just, without writing all this code, just upload the data directly to AutoML tables and do it that way. Likewise, if we go to AWS or Azure, let's go to Azure first here. Let's take a look at this real quick. And I'm going to sign in here that they have an AutoML system that is pretty good. Or let's see, I'll log into this account. There we go. And what this will show us is that if I go to the portal, they have a system called Azure ML Studio. And what Azure ML Studio does is it gives us this machine learning UI here, and I could do similar things. So I could go to their Launch the Studio, and then say, I want to do AutoML, and here's actually a successful AutoML run, and I can look at this particular model and see all the different algorithms that it ran, and look at the explanation, for example. And in this particular explanation, I think will show us multi-class classifier, 40 features. I can look at the data set explorer here, feature importance, individual feature importance. And again, this is just a point and click. And let me show you how I ran this. So if I go through here and I go to Azure ML Studio, I would go to this example. Let's just keep this. I would go to automated ML, and I would just say new automated ML run. I would say pick a data set. In this case, I had MBA data set. I could either upload it with a CSV file or pick one that was already there. And then I could just select what target. What do I want to try to predict? I want to predict, let's say, maybe the position. I want to predict which position, and then I tell it where a compute cluster runs. And then I maybe say create new experiment. We'll call this, predict position, something like this. And then again, it goes through, and I can tell it to do classification and even pick deep learning, and then go through here and say finish, and then it goes and kicks off an automated run here. And what's great about these kind of systems is that even if you do know how to write all the code to do classification, you're accomplishing the same thing, and then it saves it for you. So especially again, if you're a business student, or you're working in a capacity where you need stuff very quickly and you want results, these kind of solutions I think are very powerful solutions. Now let me show you one other thing here, which is the Dataset Explorer. And one thing that's kind of neat as well is that you can actually, one of the things that it will show you as well is you can actually visualize the whole data set here and look at the profile of it, and it'll show you like your own exploratory data analysis. So this was an MBA data set, and you can see that it shows us the counts. It shows us like a histogram of the age, the field goal percentage. So again, all I do to create one of these data sets here is I go to data set, I say create data set, I say from local files, and I say tabular data. We'll just call this, more NBA, for example. And then if I say next, I can just feed it in a CSV file. So I just click on the CSV file or even a JSON file and upload it, and then it goes and puts that data inside, and then I can do automated machine learning. So I think all cloud platforms as well are now at the point where they're able to do automated machine learning, and it's a great time to be doing machine learning because you can either do what we did, right, which is write the code yourself, go through all this stuff, or in many cases get the same results by just uploading the data, telling it which are your features, and then which is your target, and then the automated ML system will do the work. All right, so you finished ML concepts in 1 hour. Make sure you take a look at that GitHub repo, which is GitHub Noah Gift. ML Concepts is the name of the notebook. And a good way to continue to go down this path is to try some AutoML, like I showed in this example, whether it's Google AutoML or Azure ML Studio, and then also try building this out yourself. And really, I think both approaches are valid approaches depending on what domain you're in. If you're a business student, maybe you lean more towards using AutoML tools. If you're a programmer, maybe you build more of tools in Colab Notebook, but they're both great approaches, and you don't have to be a programmer with 10 years of experience anymore to do machine learning. And I look forward to seeing you in another video in the future.